All right, good morning, everyone. So, usual announcements. Friday, we have our homework due, and then there's no pre-lab number 5 today, and I think that's the only thing we need to go over this morning. What I want to do today is I want to start a new topic, and what we're going to try to do is to get a little bit of a clearer picture of what happens microscopically when we have a current flowing in a conductor. So remember, we talked about this a little bit. If you have a conductor, we could treat it as just some resistor in our circuit. If we connect it to a battery, there'll be some current that flows. The size of the current will be dependent both on the voltage difference provided by the battery and on the resistance of the conductor that we're flowing the current through. So we have this relationship that the voltage across the resistor is equal to I times R. And you did some measurements like that in lab number 4 when you had that board in front of you that had the 6 wires made of the same material, but of different diameter. And then the other little bit of information that we'll make use of is that the definition of current is the amount of charge, delta Q, that crosses some surface through our conductor in time delta T. Okay, so just to orient ourselves, where we are in the book is we're going to talk about the material from section 9.2. And so the topic is the model of conduction in metals. And so here's basically the exact same setup that you had in lab number 4. There's some conducting wire, we connect it to a voltage difference, and we could measure, say, a current. The one thing that I added in our little figure here is a switch. So we could open or close the switch. And when the switch is open, the battery is not in the circuit. There's no potential difference across the wire. When the switch is closed, that battery does provide a potential difference across our wire and establishes the flow of charge. So what I want to start with is this idea of having the switch completely open initially. So let's, with S open, there is no voltage across our wire / resistor. And the electric field inside the conductor is going to be equal to 0. Okay, and so what we can do is we can say, all right, E equals 0. And this is exactly what we previously called a conductor in equilibrium. So in this case, the conductor is in equilibrium, and there's no net flow of charge. Okay. That doesn't mean that there's no motion of the charge at all. It just means that there's no preferential motion in any single direction. So we could imagine, like, we could have an electron in here. And so here's our electron. And what happens is it is moving in some random direction, and eventually it will scatter off something in the conductor. The conductor is made of individual atoms, of course, and so the conductor can scatter off these atoms, or maybe there's some kind of impurity, some defects in the material, and so these electrons can also scatter off those types of defects. Like, you know, if this is a copper wire, maybe there's some other elements that are mixed in there just when the copper is refined at the place that manufactures these wires. Okay, so the picture is then that the electron moves off in some direction until it scatters off an atom or an impurity, and then its direction is randomized. It goes off in some other direction, and a short time later it scatters again, and it just keeps going, and it keeps having all these scattering events. Now, if there's no preferential direction for motion of these electrons, then this one electron on average doesn't move away from its original position. And so this type of motion is called Brownian motion. I think originally when Brownian motion was first studied, they had like a little solution of water and they suspended these tiny little seeds in them and they watched the motion of these seeds scatter about. And in that case, again, it was this little seed scattering off of the different atoms that make up the suspended fluid. And so it moves all over the place, but on average, it never goes anywhere. And so that's exactly the scenario that we have here. Okay. So in a conductor, electrons constantly collide with the atoms / impurities within the metal. So after a collision, the direction of motion of the electron is randomized. Okay, and so this is sometimes called Brownian motion. Now in the picture above, I drew the motion of just a single electron, but this wire is just filled with these type of electrons, and they're all doing this kind of motion simultaneously. Okay. So in this case, there is no net motion of charge in any particular direction. And that implies that the current is equal to 0. Because if you remember how we thought about current, if I put an imaginary surface through my conductor, because the charges are moving in random directions, just as many electrons cross that surface from the left to the right as do from the right to the left. And so then the net charge to cross that surface is 0, and therefore the current is 0. Okay, so now what we're going to do is we're going to close the switch. So now we close the switch S. And so if I was to redraw that, we have our wire. We're going to connect it to our battery. Now our switch is closed, so I'll just draw it as a continuous wire, like so. What the battery does is the side of the wire that is connected to the positive terminal is at a high potential. So this is a high potential side. And then the side connected to the negative terminal is at a low potential or low voltage. And we know that electric fields point from high potential to low potential. And so what we have inside of our conductor now is an electric field that points, in this case, from left to right. So now this is a non-equilibrium situation because our requirement for conductor equilibrium was that the electric field inside had to be 0. And we've already violated that condition. So the potential difference across our wire establishes an electric field in the conductor, and this field exerts a force on the mobile electrons, causing a net flow of charge or a current. Okay, and so this is a non-equilibrium situation. All right, so in this picture then, if it's my electrons that are causing the flow of current, there'll be a force on these electrons. Because the electrons are negative, it'll be in the opposite direction of the electric field. It's still true that the electrons are constantly scattering off of atoms in the wire or defects, but now, although they scatter and have their direction randomized, on top of that, they slowly drift in the direction opposite of the electric field. So if I had my electron here, maybe initially it's going in this direction, then it scatters, and we can do something like this, where it does tend to have its direction randomized, but if this is the initial position, then at some time later, it will have drifted anti-parallel to the electric field. And it's that net motion, that net drift of the electrons that results in the current. Because current is defined to be the direction of flow of positive charge, if I have electrons going from right to left, then that corresponds to a current going in the opposite direction, left to right. And so we would have a current I in this direction. Okay, so the non-zero electric field tends to cause the electrons to drift, drift to, let's say, to be general, drift in the direction opposite the electric field, which results in a current that is in the direction of E. Okay, so that's kind of the intuitive qualitative picture. What we're going to try to do is to see if we can work out some quantitative properties of this current. Okay, and so how are we going to do that? So we're going to consider a conducting wire that's carrying current I. Okay, so the picture would be, let's see, here's our wire. What I'll do is I'll draw like a little surface in here, and we're going to use this surface to keep track of how much charge crosses it so that we can calculate the current. Okay, we'll label some other things here. Let's say that our wire has cross-sectional area A. So this is cross-sectional area A. If our wires are typically cylinders, and so our cross-sectional area would be a circle. Okay, and so let's imagine that we have a current that is going in this direction I. Okay, so in this, let's say in time delta t, so in time delta t, the total charge to cross our green surface, did I do it? No, sorry, it's a blue surface. Blue surface is, well, just by definition of current is delta Q divided by delta T. So if I solve for delta Q, it's just I, the current, times delta T. And I'm going to call this equation 1. All right, and so what we're going to do is we're going to try to come up with two expressions for delta Q. We've got one of them, and we'll come up with a second one, and we'll end up saying that these two expressions have to be equal to each other, and that's how we're going to come up with this new expression for the current. All right, so in order to do that, what we'll do is we'll consider a positive charge Q moving with a drift velocity Vd in the direction of the current. Okay, so what I'm going to have is a charge Q here, and it's moving with some drift velocity. And so that drift velocity is due to the electric field that's inside the conductor. So I haven't drawn it, but we have to imagine there's a battery connected to this wire. It creates a potential difference, which makes that electric field, which causes the flow of charge. All right, fair enough. So what we have to do is we have to come up with an expression for delta Q, the amount of charge to cross that surface, that blue surface. So in a time delta T, our charge Q moves a distance delta X is equal to whatever its drift speed is times delta T. Okay, so that's simple enough. If it's moving to the right with speed Vd and we wait time delta T, the distance it's moved is just that speed times the amount of time. All right. So what I want to do is I want to imagine that in this time delta T, this charge Q has moved from its current position to that blue surface. So it just barely crosses that surface or reaches that surface in time delta T. If that's the case, then this distance is delta X, the distance that it moved. Okay, but if that charge, a distance delta X away, reached the surface in time delta T, then any other charge that is between the blue circle and the black one is also going to cross that blue surface. And so if we could count how much charge is inside this kind of shaded cylinder, that's the total charge that will cross the surface in time delta T, and we can use that to make a second equation for this delta Q thing that we're trying to do. Okay, so any charge to the left of the blue surface, but within distance delta X of it, will also cross the surface in time delta T. Okay, so what we have to do is we have to count the number of electrons that are in the shaded part of this cylinder. So the shaded volume is the cross-sectional area of the cylinder, which we labeled A, times the length. And so that length we've labeled as delta X. And so that shaded volume is the cross-sectional area times delta X. One property that you could look up for different conductors like copper, aluminum, tin, whatever other metals you can think of, is you can look up the number of mobile electrons per unit volume. So that's a number density. So if we know the number of electrons per unit volume, and now we have a volume A delta X, the product of those two tells us the number of electrons that are in that shaded region, and that's the number that will cross the surface in time delta T. Okay, so if the conductor has it's called an electron number density, electron number density. It's usually given the symbol little n. And so this is going to be the number of electrons divided by the volume that they occupy. So if that's the case, then the total number of electrons in our shaded region is, okay, so we'll use big N. I'll put a little subscript E, so that's the number of electrons. So this is the number of electrons. It's going to be given by the number of electrons per unit volume. So this is number of electrons divided by the volume they occupy times A delta X. And so this is the shaded, shaded volume. Okay, so now we have an expression for the number of electrons that are going to cross our surface in time delta T. Okay, so this is, maybe we could be more detailed. The number of electrons that cross our surface in time delta T. What we really want is the charge to, the amount of charge that crosses our surface. Well, if we know the number of electrons and every single electron has the exact same charge, usually denoted little e, it's 1.6 times 10 to the minus 19 coulombs, then this Ne times the charge tells us delta Q, the amount of charge to cross our surface. So since each electron has charge E, delta Q is equal to E times the number of electrons, which is E times, what was it? The electron number density times the cross-sectional area times delta X. So this is the charge crossing our surface in time delta T. Okay, so we're pretty close to where we want to be. We have an expression for delta Q. I want to make one more change, and that is I'm going to replace delta X, which is the distance the charge travels in time delta T, with its drift velocity times delta T. Okay, so that's how we find that delta X. And so finally, what we have is delta Q is E times little n times the area times the drift velocity times delta T, and that's equation 2. So what we're going to do is we're going to say equations 1 and equations 2 calculate the same quantity. They must be equal to each other. Let me just remind you of equation 1. It was a really simple one, right? Equation 1 said that the total charge crossing our surface is just current times delta T. Okay. So equations 1 and 2 calculate the same quantity and must be equal to one another. So from equation 1, we say I delta T is equal to equation 2, which is E times little n. I'm going to rearrange this. I'll put a VD here, A delta T. And then finally, we can cross off the delta T's, and one of the expressions we wanted to get today was this expression for the current. And so there's a current, which is like a quantity that we can measure in a lab that is expressed in terms of some microscopic properties of whatever conductor we're using. And those microscopic properties are the charge of the charge carriers, which is the electrons, their drift velocity, and also the number of electrons per unit volume of the copper. The other thing that's in there is the cross-sectional area of the wire. And in fact, if this cross-sectional area is a circle, then this is like proportional to the radius squared or the diameter squared. And that's exactly what you saw in lab number 4 when you were measuring these little wires. You measured their resistance, which just depended on the current, and you saw that the resistance was proportional to 1 over the square of the diameter. And that comes from this factor of the area in this expression. Okay, good. So the other thing we could do is we could say, well, maybe we want to know the drift velocity. And so if you wanted to know the drift velocity, we could just express it in the following way. We could just solve for the drift velocity in this way. So let's do an example. For a copper wire of diameter D is equal to, say, 1 millimeter. And let's see, I is equal to 1 amp. What is the drift velocity? Okay, so what we're going to need to know is we're going to need to know little n, the number of electrons per unit volume for copper. So for copper, the electron number density is n is equal to 8.3 times 10 to the 28 electrons per cubic meter. And so if you just think for a minute, like that's a huge number, okay? So, you know, you may have done chemistry or something like that. And so you talk about Avogadro's number all the time. Avogadro's number is like 10 to the 23. This is it's 100,000 times more than Avogadro's number. So if you had a cubic meter of copper, there's an enormous number of free electrons that are available to carry your current if you provide voltage difference across the material. So anyways, the other thing we need to know is the charge of the electron. That's 1.6 times 10 to the minus 19 coulombs. So this is just a plug-in numbers type of question. So we need to know the current, which we're given 1 amp. We need the charge of the electron, which we just wrote down. We need the number density, which we have. And for our area, if this is a cylinder, the cross-sectional area is a circle. Area is pi r squared, or it's pi times the diameter divided by 2 squared. And the diameter was given as 1 millimeter. If you plug in these numbers, it comes out to be 9.6 times 10 to the minus 5 meters per second, or that's about 0.1 millimeters per second. So that would mean that for that current in this wire, it would take the electrons 10 seconds to move 1 millimeter. So that leads to a question then, like why, like 1 amp is probably typical of sort of some of the currents that are running around through the wires in your house. So why is it then that when I play with a light switch, I don't know, can I play with a light switch in here? No, okay, I could do something. This is not a good, I didn't want this gaming. Oh wait, this is bullshit. All right. If you had a normal light switch in your house, you flip it off, the lights go off instantly, you flip it on, they come back on instantly. So if it takes charges so long to move a short distance, why is it that the lights come off and on instantly when you flip a switch? Any ideas? So think about, yeah, go ahead. Sorry, it moves what? Yeah, it moves a very short distance. So if your switch is far away from your light, why does the light come on so fast? Yeah. Yeah, but this is the copper wire. Your house is filled with copper wires, and so this is typical of the speed in your house. Yeah. Yeah, that's right. It's a collaborative effort of the electrons. So if I have an electron density in my copper wire, I have electrons evenly distributed throughout the entire wire. So if I move one at one end of the wire, like one way to think of it is it moves a little bit and then it repels all of the charges that are in its vicinity, and so they move. And then those ones that move repel those other charges, and so they all move together. And the repulsive force due to the electric field that one electron creates and exerts forces on the next, that moves very fast. Electric fields are moving at the speed of light, so it's almost instantaneous. Okay, good. So how are we doing time-wise? Oh, good, we got 20 minutes left. So what I want to do is I want to return to this expression, this new expression for the currents that we just worked out, En times drift velocity times cross-sectional area. And so what I want to notice about this is that this expression for the current depends on the geometry of the wire, the cross-sectional area. So let's note that I depends on the geometry of the wire because of this factor of the cross-sectional area. So sometimes it is convenient to define a current density. The current density, we're going to give a symbol J, and all it's defined to be is the current I divided by that cross-sectional area, and so then that's just equal to N times the drift velocity times the charge of the electrons. Okay, if you encounter the current density when you're reading your textbook or looking online, this current density is also often expressed as a vector. So that means it has a magnitude, and the magnitude is exactly what we wrote down here. But it also has a direction, and its direction is defined to be the direction of the current in the wire. So let's note that current density is a vector with direction in the same direction as the drift velocity, which is equivalent to the same direction as the current. Okay, so what we could do is we could express this current density as E times N, and we can make our drift velocity a vector. Okay, and that's pretty normal. Velocity is usually expressed as a vector. Okay, so for some materials, what we're going to try to do in the last 15 minutes or so is we're going to try to recover our expression for Ohm's law. Ohm's law is that the voltage is proportional to the current in a conductor. That's not true for all materials, but it's true for a lot of materials, like the metals that we're talking about now. And thus far, we've only written that down as an observation, and the constant of proportionality between the voltage and the current is the resistance R. And so we're going to see if we can come up with a microscopic picture of where Ohm's law comes from. So for some materials, like metals, the current density, J, is proportional to the electric field, E, in the wire. Now, if you think about that, that's maybe not too surprising, because current density is this flow of charge. The charge flows because we establish an electric field in the wire. And so you could imagine that if you make a stronger electric field by using a bigger battery, then the force on the charges gets larger, and then they move with a faster drift velocity. And so that's what's happening here. If that is the case, then we could say J is proportional to the electric field strength, E. And if they are proportional to one another, that means they're related by a constant of proportionality. And so the constant of proportionality is called the conductivity, and is given the symbol sigma. So this is Greek letter sigma. It's unfortunate, but unavoidable. We've already used sigma for a different meaning. When we were doing things like Gauss's law, we said sigma was representing a charge per unit area. So it's too bad that they're using the same symbol for two different things, but that is convention. We're powerless to change it. So in this case, sigma is the conductivity. Okay. So that means if that's the constant of proportionality, we could express J is equal to sigma E. Okay. So materials for which this proportionality holds are called ohmic materials, and they obey Ohm's law, which we're going to try to write down in just a second. Okay, so let's see. We know that J is equal to I over A. That's how we define current density. So that's one expression. We had equations 1 and 2. Let's call this equation 3. Okay. So what we're going to do is we're going to take equation 3A and we're going to sub it into 3. And I want to make one more substitution into equation 3, and that's going to be for the electric field. So in order to do that, let's consider the following conductor connected to a battery. So we'll have a wire, we'll say it has a length L, and I'll connect it to a battery here, positive terminal, negative terminal. This battery supplies voltage delta V here. I'm gonna move this over here so I have some more space. Okay, so this is the battery delta V. And the battery establishes an electric field. So I want to come up with a relationship between the electric field and the voltage of the battery. Fortunately, we already know how to do that because we could calculate changes in potential or changes in voltage when we move through an electric field in this way. And so we imagine we start at 0.1 and then we end at 0.2, and we want to know what's the change in voltage. Well, to make this simple on ourselves, let's just assume that the electric field inside of our metal is constant. So if we assume that the electric field in the conductor is constant, and we're going to move in the direction of the electric field. So if I move from 0.1 to 0.2, I'm going exactly parallel to the electric field. And so E dot ds is just E times ds. If E is a constant, we take it outside the integral. So we have E times the integral of ds. ds is just the distance we move, which is the length L. So if we assume the electric field in the conductor is constant, then the absolute value of this voltage change can just be expressed as E times L. And that means that E is delta V, delta V divided by L. Where I'm just going to ignore the sign. I only care about the absolute value of this voltage difference for this argument. And so this is going to be equation 3b. And so how much can I get on here? So I'm going to take 3b, which is an equation for E, and 3a, which is an equation for J, and we're going to substitute that into equation 3. Okay? So let's sub 3a and 3b into 3. So 3 was J, which we're going to write as I over A is equal to sigma times E. And for E, we'll write this as delta V divided by L. Okay. What we'll do is we'll solve for delta V, the voltage across the wire. So let's solve for delta V, which is the voltage across the wire. All right. So let's see, if we did that, delta V is going to be equal to what? There's going to be a factor of I, and then we have to divide by sigma, so we'll get a 1 over sigma. We'll have to multiply by L, so we'll get an L. And then we still have a 1 over A that's left over, so we'll get a 1 over A here, like so. All right. Let's compare that to the very first thing we wrote down. In fact, we could go back and find it. The very first thing we wrote down at the beginning was this expression where the voltage across our resistor or in a wire, which is acting as a resistor, is just I times R. So now we've got another expression for that voltage across the wire, and it's right here. This must be equal to I times R. This must be equal to I times R. And so that means that all of this is R, the resistance of our wire of length L and cross-sectional area A. Okay, so R is 1 over sigma L over A. And this makes intuitive sense if you think about it a little bit. R, the resistance, a high resistance means low current in your circuit. So if you have a high resistance, that comes from very long wires. So imagine trying to push current through a really, really long wire versus one that's really short. It's going to be easier to move the current through the short wire. You can think of this in terms of the hydraulic analog. If you have a pipe, is it going to be easier to, or just think of a straw, okay? You're go to Mickey D's and you get a milkshake, and so it's really thick, and you start with like this really long straw. You try to suck the milkshake through the straw. You have to suck really hard. You have to give a big pressure difference to drive that through this long straw. But if you take your straw, you cut it in half, you'll have to suck with half the effort to get at your milkshake. Okay, so that makes sense. There's also a factor of 1 over A. So that means when the area gets small, the resistance gets large. Again, you can think of your milkshake. If you want to suck your milkshake through a fat straw, you're going to get more of it more easily than if you try to suck it through a very narrow one. And the same thing happens for trying to push charge through wires. It's easier to flow charge through a fat wire than it is through a skinny one. And then the conductivity, that's just a property of the conducting material. So the conductivity is going to be determined in part by the number of electrons per unit volume. So materials with high electron densities are going to have more higher conductivity than ones with lower electron densities. Okay, so this delta V equals IR. This is, as you may already know, that's our expression for Ohm's law. And I just want to emphasize that it's not true for everything, but it's true for a lot of common good conductors that we find in, say, wires in our electronic devices and homes and just metals in general. Okay, so we have 2 minutes left. The last thing I'm going to do is I'm just going to write down, let's just do some unit type analysis. Okay, so we know the units of R is ohms. Resistance is measured in ohms, okay? And so from Ohm's law, delta V is IR. That means R is delta V over I. So 1 ohm is also equal to 1 volt per amp. Okay, so that means the units of sigma, let's see, if we solve for sigma, that would be 1 over R times the units of L divided by the units of area. And so that is going to be, let's see, meters for the length, ohms for resistance, and meters squared for area. And so we can cancel one factor of meters. And so this is 1 over ohm meters. So the units of the conductivity sigma is 1 over ohm meters. Okay, so sigma is the conductivity. The last thing I'll do is You may have seen resistance expressed in another way. So often, resistance R is expressed in terms of resistivity rho, which is just 1 over the conductivity. So if we take our expression for R in the top left corner and we replace 1 over the conductivity with the resistivity, then that is another way of expressing the resistance rho L over A. The units of the resistivity is just 1 over the units of the conductivity. Conductivity is 1 over ohm meters, and so resistivity is ohms times meters. Okay, so that's what I wanted to do about our microscopic description of current. What we'll start doing on Friday is starting to analyze probably some simple circuits involving batteries and different combinations of resistors. All right, thank you very much.